In this video, we're going to take a look at our next presentation, which demonstrates various ways to access memory in C++. Essentially, computer memory consists of consecutive numbered storage cells. So this is a pretty simple idea that memory has locations which could be accessed by simply allocating variables, taking addresses of these variables, and then modifying these variables in memory, which uniquely are identified by their location. Each memory cell has a unique address. Understanding memory is important because CPU instructions really rely on memory addresses when the program executes. So basically, behind a C or C++ code like this, there is a lineup of CPU instructions which our compiler compiles, and we can actually look at the disassembly to visualize these instructions. If we running a debug version of our program and stopping in debug environment, we can go to disassembly and visualize the actual instructions. It's interesting observation that only one instruction, add, deals with the math. This is the actual addition. The rest of the instructions move, transfer values to and from memory to realize this computation. Again, this was our code that we used, and I can show you very quickly in our demo project. Just copy and paste the code, make the white space alignment, save it, build this program. I'll notice that it's using x64. I'll switch to x86 to be consistent with our presentation and rebuild it again. And now this program does not interact with the user, but I can set a breakpoint by simply clicking on the margin in my source editor and say, let me stop and see what the actual instructions corresponding to these statements look like. So now I need to go to debug and start debugging. You can see that the command window for this program opens. This is a console application, so it requires the creation of console. The console is created, however, it doesn't interact with the user, doesn't print anything. What happens instead, we're making a stop in this debugging environment, and this little arrow indicates what is the next statement to execute. So I can press F10 key in Windows, Microsoft Windows Visual Studio here, and step over the line. So now I'm looking at the actual example of addition, and if I want to see my instructions, what I can do is in my source file view, I can right click and go to disassembly. This option will switch to disassembly. In the disassembly window, you will recognize something that looks like what we were showing in our slide right here. There are 3 instructions, 2 move instructions, and 1 add instruction, which shows us that with respect to this addition of 2 variables, we have indeed 2 move instructions and 1 added instruction. So basically, when we look at this low level and try to understand it, of course, we have to be aware of the addresses of these variables and how exactly compiler decided to use these addresses when using all of these instructions and all of the resources that it has to be able to do the computation. Can CPU add 2 memory values in one step? So instead of using 3 separate instructions, could it do it in one step? And the answer is really no, because what happens is that CPU can only access one memory location per instruction. This is a limitation of the most modern CPU architectures, and the fact is that it's using all of its power, whether it's a 32-bit platform or 64-bit platform, to use it as a memory specification when it has to specify where in memory the data is, and use the data line or data bus to be able to communicate to that memory location. In other words, there is a limitation on the CPU that only one memory location can be accessed at any given step, which is represented by an individual CPU instruction. It's just a quick observation about memory access by the CPU itself. So in early days of computing, programmers were writing machine instructions in binary codes. So this predates assembly programming language, which adds mnemonics to CPU instructions. It was just back in the day where everything had to be coded in a really hard way using just zeros and ones. So we have like a 2-byte instruction here, possibly the move instruction, for example, and the first part of this instruction would specify the code of operation, right? Just as an example. And the second part of this instruction could specify location in memory. So then, on paper, these machine codes looked pretty difficult, pretty unreadable. So the programmer developed a technique to add some more distinguishable elements to the syntax, such as square brackets, just to delineate a structure of this instruction, that this is an opcode and this is the actual memory location. Modern assembly languages retain square bracket notation. Some of them are using actually parentheses, but you can see that when we observe this instruction in our CPU, such as this right here, move double word at the location of variable y into register EAX, which is just an accumulator register memory location directly inside the CPU. This variable in our debugging environment really translates to this address, the actual address that there is. So from the assembly perspective, y is actually the location of a variable y in memory. And here the suffix b indicates that to the assembly that this is a binary value. Just another example of history of machine languages and assembly languages where binary codes were used, and we're trying to compare these binary codes to mnemonics that modern assembly languages add to this level of programming. So let's consider something that uses memory access syntax in C. Because C is a systems programming language, it must provide direct access to physical hardware, including memory. And C supports assembly style to access memory, and I'm specifically talking about the use of square brackets. Basically, the use of index operator or subscript operator, which is denoted by square brackets, always indicates an access to memory location. And we can see this in syntax of arrays, and we'll probably talk about that syntax in a little bit, but this is the idea. So you can see that the roots of the syntax are coming from assembly languages and early days of programming. And let's take a look at this sample and its logic. So we're trying to start at the beginning of memory. So we're establishing some kind of integer value which is simply set to 0. And we say, okay, in this array of memory cells, we would like to access location number 248. So we use another integer and we say, okay, let's use that location. So the way C syntax deals with memory access, that you have to have some kind of base address, which in our case is just a 0, and then an offset from that place. And it has to be combined together, because so often we are dealing with blocks of memory that we need to start at the beginning of the block of memory. In my case, I just initialize it to 0. And then we're specifying how many steps away from this initial location we would like to go. And so this expression refers to location in memory, and this is an example of memory access syntax in C. So what we do next is that we just use this as a target to store integer 65. Likewise, we can use this location, access this location in the next statement, and retrieve this value and store it in some other variable and continue with our coding. So this code would compile just fine on an older machine such as PDP-7. This is an example of this computer, PDP-7. And it was the world's first Unix machine, usually originally Unix spelling, a sarcastic reference to Multics, which was a different project, but it originated by Dennis Ritchie and Ken Thompson of Bell Labs in 1967. So a lot of the syntax that we are using in C and C++ today dates back to these years on 1967 and early 70s, where Unix was starting to grow. So PDP-7 was an 18-bit machine, and it was notable for its solid construction weighing half of a ton. All right. So the Multics project that I mentioned was a multi-user, multi-processor platform-independent operating system attempt, which was developed by a combination of companies and started even earlier. So the design of Multics greatly influenced the design of the Unix operating system. If you're familiar with Unix or Linux, you know that everything can be accessed from a shell, and you can use hierarchical nature of file system to access all devices and files and all other objects on that computer. So what has to change in the modern version of C and C++ with respect to that uniform 18-bit memory organization of the original PDP-7 machine? Very similar, very similar code. The only thing that was added here is that we have to provide explicitly to the compiler information that specifically tells us that this is a location of a character, or location of an integer, or location of some other type. Because remember, when we're specifying just memory addresses like this through zeros and other numbers, compiler has to know what kind of objects we're trying to update in memory. And character would be 1 byte size, an integer will be 4 byte size, and double will be an 8 byte size object. So therefore, a compiler really needs from us a clarification on what kind of location is this. And this is the syntax that's being used